All right, so today we're going to talk about analysis of covariance, and we've got a little bit of new terminology here. First thing we're going to talk about is what do we call a covariate, or what do we mean by a covariate? You also hear people refer to this as a nuisance or a concomitant variable. And what it is it's an observable variable, but we can't control it. It's just something, it's like baggage that comes along with whatever our experimental unit happens to be, that is naturally associated with the response variable we're trying to measure. So what we do is we try to measure this covariate at or about the same time that we measure the response on somebody or on some experimental unit. So some examples here are, peak heart rate and a covariate of age. Anybody that's been on an elliptical machine or any of the machines at a gym knows that the peak heart rate goes down as your age goes up. We also have something along the lines, you think of oxygen saturation of a person that smokes, so maybe pack years could be a covariate there that could explain why oxygen saturation levels are low, or salivary continin, and that would be a direct function of the covariate cigarettes per day that a person smokes. So ANCOVA itself is another one of the linear modeling techniques, and what it does is it basically fuses ANOVA and regression into one big model. And the whole goal here is to, by allowing the mean to slide with this regression component, rather than just fitting a single mean to each group, we're allowing it to slide within the group based on some covariate value. I'm decreasing the amount of unexplained variation, and thus I am improving my unexplained variability, or I'm making my precision better. And if I have better precision, I end up being able to detect smaller and smaller differences. So real quick recap for the ANOVA model. We have a couple of different ways to go. We have the means model, which is the first one here. This y sub ij equals mu I, that's the cell mean, plus e sub ij, so that's the cell means model. Or we can also talk about it as an effects model, where we have some global mean shared across all cells, plus a tau I, or the effect of being in whatever group or whatever cell, plus this e sub ij, which is the random deviation for each observation that I see from the cell mean. And those e sub ij's are assumed to be distributed with a normal distribution with a mean of 0 and a standard deviation of sigma squared, or excuse me, and a variance of sigma squared or a standard deviation of sigma. And that sigma is the same standard deviation regardless of what group you're in. So if I go across and I do the expected value of any y, it comes back to be the cell mean for whatever group it's in, or I could look at it as the global mean plus the effect. And if I go to look at differences across two groups, what ends up happening, regardless of which one of these I'm looking at, the reason we like this, concept of the effect of a group, or the effects model, is that when we go to subtract this, the mu's, the common component, subtracts out, and then we can talk about this tau 1 minus tau 2 as being our effect that we're interested in. And then with the regression model, similar setup, only now it looks like the standard equation of a line that we've seen, probably since 8th grade. So my y sub I, so this is for pair I is, or y and x are paired or linked, is equal to alpha plus beta, my slope or the effect, of my covariate x sub I plus my e sub I. And again, these e sub i's are assumed to be normally distributed with a mean of 0 and a variance of sigma squared. If I take expected value across y, I can do it for an expected value of y given some value of x is going to be equal to my y-intercept plus my slope effect, or the coefficient, if you will, of x. And that gives me my expected value at that point. So in other words, the expected value in regression slides based on what the value of x happens to be. And again, that's just read, the expected value of y given x. Now ANCOVA, what it does is it assumes that your response and your covariates are both quantitative and continuous. It also assumes that the association between the response and the covariate is linear. So we're going to have to look at a box plot between our response variable and our covariate to determine, is that linearity, met. And then we assume, again, the same thing we did for regression, the same thing we do for ANOVA, only now we have to say that the errors are distributed normally with a mean of 0, and the variance is constant across all levels of my covariate, so no matter what value of x I'm looking at, and every level of the explanatory factor. So any way I can mix and match those pieces together, the variance is assumed to be constant across. And then the explanatory factors themselves do not affect or influence the covariate. So what that's saying is that if I do an ANOVA with the covariate as my outcome, the explanatory factor does not account for anything. It is not significant, if you will. And then a simple ANCOVA assumes that the slope itself within each group is constant across all levels of the explanatory factors, and the only thing that changes is where that line is positioned within the data based on whatever group membership I'm in. And this particular assumption here is actually testable. So the ANCOVA model comes in two different forms. There's what's known as the simple model, and then there's what's known as the centered model. And the simple ANCOVA looks a lot like a regression model, although you'll notice that instead of sticking in here the alpha for the y-intercept, I have this thing I'm calling mu I star. And what mu I star is really kind of a glorified cell mean, if you will, in context from our means models previously. So this y sub ij is equal to this value, or this intercept specific to group I, plus my coefficient times the covariate, so the effect of the covariate sliding, and then I have this e sub ij, just like I had before. E sub ij is going to be normally distributed with a mean of 0 and a constant variance sigma squared. And I can think of mu sub I star as equal to some global mean mu plus this alpha piece, right? So I have the global mean from the cell, I've got this alpha piece from my regression, plus this tau I. Now in reality, I can't tease these two apart. I cannot tease mu from alpha. So I basically have to treat this as some value that I can estimate in together but can't separate. So I'm going to call it mu star. So I'm going to have some global intercept that's common to all models, and then I have an effect, this tau sub I, being added in to say what group membership, or how does this group deviate from another group. But then I'm assuming right now in the simple model that all the slopes are constant. So once I set my y-intercept, all the lines have exactly the same slope, or all the lines are parallel. So what does this tell me? Well, the y-intercept mu star plus tau I, which would be the expected mean response at a covariate value of 0, has potential problems in that a lot of times what we are looking at in our types of studies in healthcare and in other public health and things like that, we do not see actual covariate values of 0. So if I think about age, I rarely see a value of 0 because almost all of our studies are done on adults, that kind of thing. So we've got some problems there. The y-intercept may or may not mean anything, just the same issue we had with regression. The adjustment, when we talk about adjusting for a covariate, is due to this beta. Again, what we're doing is instead of fitting a single mean to the groups like we do in ANOVA, we're saying we're going to fit a sliding mean. So this regression concept, we allow the mean to slide relative to its covariate value, and for every unit increase in my covariate value, the mean slides by beta. So beta could be a positive sign or a negative sign. It's going to slide whichever direction. So in other words, the expected value of an outcome now depends on the value of the covariate itself. So, but typically what we're really after is what is tau 1 minus tau 2. And I notice, even in the ANCOVA model, if I evaluate both groups at the exact same covariate value, I end up with mu star plus tau 1 plus beta x minus mu star plus tau 2 plus beta x. When I distribute the negative sign across, I end up with mu star minus mu star, so those just cancel. I end up with beta times x minus x, but we're evaluating it at exactly the same covariate value, so that goes to 0. And all I'm left with is tau 1 minus tau 2. So I can still get at structurally what I'm after when I do a simple ANOVA, but this one is allowing me to do it with more precision and therefore find a smaller and smaller difference as being significant. Now, one thing I do want to point out is the expected, even though I'm using tau 1 and tau 2 everywhere, the expected value of y given x comma tau I is not equal to the expected value of y given tau I. So in other words, the ANCOVA model does not equal the ANOVA model when we're talking about our taus necessarily. All right, so here's the ANOVA concept, or ANCOVA concept, excuse me. What I am trying to do, this is a simple one with common slopes. And so we see our lines are parallel. And what I'm after is I'm fitting, in this case, in the blue group, I'm fitting a line to the blue group, and I fit a line to the green group. And let's say if I bring this down, the y-intercept, if I keep going, is probably about, I'm going to guess 0.6 or something like that. And then this blue one is shifted up by a certain amount. Well, how far those are shifted is literally the difference everywhere, no matter what the covariate value is, because I have constant slopes. They're parallel. So any vertical distance here is the exact same vertical distance here, or perpendicular distance are always the same. Doesn't matter which way I look at. As long as I'm looking at parallel lines, the distances stay constant. Okay, so phrases to look for if an ANCOVA may have been used. So after controlling for, insert the covariate name, differences in, insert your explanatory variable, and then they continue on with their sentence. Or the following covariates were considered, or results were adjusted for, that type of thing. So those are words you can look at, or look for as you're driving, or phrases I should say, that you can look for as you're going through and reading journal articles to see, did they really adjust, or what were they doing. So here's an example we're going to use for implementation. This is data taken from a study, it was a wildlife study done by D.E. Walshag in 1957, is looking at an Arctic whitefish that can live in freshwater or in lagoon water, which typically tends to be salt water. And the idea was to look at, is the metabolic rate different between fish in a lagoon environment or fish in a lake environment. So here's the data that I'm concerned with. There's 22 observations, 8 in the lagoon, 14 in the lake. The outcome here is the natural log of oxygen consumption, and the covariate that they want to take into account is a measure of the size of the fish. So what they chose to use was the weight of the fish as a surrogate for the actual physical size of the fish, and they also log transformed the covariate. So if I was going to do this just as a straight up ANOVA and ignore the covariate, I could go through and do my ANOVA in SPSS. You probably have done this already for your projects. So analyze, general linear model, univariate. You can select your outcome, select your grouping variable, go into your options tab and select descriptive statistics and parameter estimates. That's going to give you the full amount of tables. And then you can save under the tab for your fit requirements. You can get the predicted values, the unstandardized residuals, and the standardized and studentized residuals if you're interested in looking at all of those. So if we run this as an ANOVA on the fish data, this is what ends up happening. I get my descriptive. So the lagoon is 1.54, has a mean natural log of oxygen consumption of 1.54, and lake has a mean natural log of oxygen consumption of 1.43. And my ANOVA table comes out looking like this. We typically don't care about the intercept line here, and with the general linear model, we're not necessarily interested with the corrected model piece. What we want is environment, and does it have an effect? And right now, based on our significance level of 0.05, it doesn't appear to, because our p-value for environment is 0.093. And we have an estimated unexplained error of 0.019. And we come down here and we see that our R squared, or the amount of variability adjusted or accounted for in the outcome by this model, is only 13.5%. We can come down further and look at the parameter estimates for this particular model, even though we know it's not significant. What we see is that the y-intercept is 1.4 and the effective lagoon is 0.109. So if I look at this, my intercept is 1.43, which happens to be my mean of the lake. And if I add on the 0.109, I end up with exactly the mean of the lagoon. So this is the global piece that's shared across all groups, is the 1.426. And then the effect of being in lagoon would be interpreted as the 0.109. Of course, whenever we do an ANOVA, we should check our model fit. So we come through here and we look and we realize, well, there's one observation here that's a little squirrely, but otherwise the distribution of errors doesn't look terrible. It's a little bit bigger here, but it's not dramatic. That same point that's low here is causing a low here and skewing my distribution of my residuals. So it doesn't look perfectly normal, but when I look at QQ plot, I see that it doesn't look horrible, other than, again, that one point's just really causing some problems. And then if I look at the box plot of the residuals, I see that it's fairly symmetric by box plot. But again, that point down here in the left-hand corner is really causing some issues. And again, it shows up as an outlier here. So we might have a few problems. But what is ANOVA actually doing? Remember, all ANOVA does is fit a mean to each group, which is what is represented by these big or thick bars with the respective colors. So I got lake and lagoon. And if I look, this is the difference of the 0.109 that is estimated between lake and lagoon that we found to be insignificant using ANOVA, but this is what ANOVA is testing. It's just trying to find out what is the difference between these two groups. Now you're probably saying to yourself, why don't I just do a t-test? It'd be much more straightforward. It would, but this is just an example. You can do ANOVA when there's only two groups, but again, ANOVA in this situation is literally a glorified t-test. So the ANCOVA process, if we want to try and take into account our covariate, is a little bit different. What I need to do is plot my response versus the covariate to determine the linear trend. And typically you want to use a separate color so that you can see, does a line fit within each one, because I could actually end up with, if I don't take into account color, something that looks like a big blob and miss the linearity that's actually going on within the data. After that, I want to check for the relationship between the covariate and the explanatory factor. So I actually use the covariate as the outcome, the explanatory as the explanatory variable in an ANOVA, and determine if there's a significant relationship there. And then once I do that, I'm going to do what's called checking for differing slopes. And we'll talk about that in a minute. And then also, since we're always assuming normality, we need to check our line assumptions with regard to any linear model. So here's the plot. You can create this in SPSS. You see I have a blue section for the lagoon, and I've got red dots representing the lake. And this is the point that's causing the problems in the ANOVA. This one is what is causing the issue. It's low in Y, or in oxygen consumed, relative to its value in X, relative to its weight. It's consuming low oxygen. So maybe this is a fish that swims marathons or something like that, so it doesn't consume as much oxygen. Or it, maybe it's a vegetarian, I don't know. It has a reason that it's not consuming as much oxygen as the other fish in this environment. But so if I come in and look, I could, except for that point, I can kind of see where I could put a line in the red. Its correlation is probably not great, but it's not horrible. And I can see where I could probably put a line in the blue, ignoring the red dots that are around there, just looking at the blue. I could probably see a line. So it seems reasonable that we can call these two linearly related. So then how do I do this? I go into the generalized linear model just like I did for ANOVA, only now in that section when the pop-up window comes in, you actually populate the covariate with whatever your covariate is. In this case, I just called it X for simplicity. It's actually the natural log of weight. So we go through and we end up with the same thing. I end up with an ANOVA table, and again, I'm not necessarily interested in the intercept or the corrected model piece. What I'm after is what is the effect of environment, and what is the effect of error, or what is my error. I'm sorry, I'm on the ANOVA. This is the ANOVA for the covariate as being the dependent variable. So again, I'm still not interested in the two tops. What I'm actually interested in is an environment. And what I want to know, is the environment significantly associated with my natural log of weight? And I see that my p-value is 0.316, so I'm not too worried about it. I come down here. Now keep in mind we only have 22 observations. My normality is maybe a little suspect down here, but it's not horrible. It looks pretty decent for so few observations. The R squared is only explaining, we're only explaining 5% by taking into account group. And my errors are pretty well evenly distributed. So overall, the ANOVA fits pretty well, and there is nothing going on based on this. So it's okay to move forward with the ANCOVA process. So the next thing I want to look for is check for a differing slope. And what that means is I need to check for this environment by natural log of weight interaction. So I literally plug that piece in to SPSS. So when you open up your SPSS pop-up window and you click over on the right hand side model, it's going to open a new window that says build the model. So you want to click on custom build the model, and then you'll go down to the center of that box, you'll click on main effects, add in your X, add in environment, and then you come down and click on that center window again, click on interaction, then highlight both X and environment and push the right hand arrow, and that will put the interaction term into your model. And then you can just go ahead and hit OK, and it'll run it. And what happens? Well, again, we're not interested in the corrected model or the intercept, but I am interested in the effective environment. I am interested in, I'm not interested in environment, and I'm not interested in X at this point, because the only question I have right now is is there any indication that the slopes are different? And that's what between the environments, and that's what this thing is testing. That's what this interaction tests. So I come across and I look here and I say, well, 0.152, the p-value for testing this differing slopes, and that's greater than 0.05, so there's no indication that the slopes are different. So the hypothesis that I'm testing when I do this is that is there some effect of taking into account environment by my covariate value? So my null is that that effect doesn't exist, and my alternative is that it does exist. And since my 0.152 is greater, 3 times greater than my significance level, I'm going to say I fail to reject the null hypothesis. There's no evidence that these are different. So I can take this term now out of my model and go back to my simple model. Okay, so since there was no evidence of a differing slope, I run the common model, slopes model, so you can just go back to the same generalized linear model dialog that you had before. All you need to do is delete the interaction term from the model statement. And once you do that, you run it, and now we are interested in looking at the effective environment. We are interested in looking at the effect of the covariate. And we come across and we see that, okay, environment is now significant, whereas when we did just a straight up ANOVA, it was not. And we see that taking into account the covariate is also important. So after accounting for the natural log of weight, the environment, based on this p-value of 0.002, does have an effect on metabolism. So if I compare the r squared from my ANOVA model to the r squared of my ANCOVA model, I see that my ANCOVA model now explains about 4.5 times the amount of variation in natural log of oxygen consumption than ANOVA did. The original ANOVA r squared was 0.135. The ANCOVA r squared is 0.602, or basically 60% of the variation in natural log of oxygen consumption is being explained by taking into account the covariate and the environment. But before we get ahead of ourselves, we need to check our assumptions as always. And when we check our assumptions, we see that we still have this one data point that's a little bit squirrely, and it's now pushing my line down below, or my dots down below my line for normality. So is that a huge departure? We can argue that, but we still see some issue. So normality might be a little suspect. When we look at our symmetry, the symmetry of our residuals looks pretty good. So whether it's normal or not, it is at least appears to be symmetric with this one outlier, and you can see that that's observation 16. And if I look at my residuals, if I didn't have this observation 16 in there, potentially this one, but if I didn't have this in there for sure, it doesn't look horrible. There's a little bit of possible pattern, but it's not terrible. So the current model as built, with the parameter estimates being spit out, would be that the expected value of y given a covariate value of x and a specific environment is equal to negative 0.068 plus 0.155, the effect of being in the lagoon environment, plus 0.653 times the natural log of weight. So that 0.653, for every unit increase in the natural log of weight, my natural log of oxygen consumption increases by 0.653. Okay, so there are two data points in the lake environment that are actually throwing the plots off. When you run this in SPSS, you don't see the types of plots that tell you what the second point is. We don't cover in this particular class, so I'm going to ignore it here, but there are actually two. But the one that we could identify with the SPSS output is data point 16, and it happens to be influential. And where it's influential is the fact that its natural log of oxygen is relatively low given its weight, the weight of the fish that reading was taken on. So one thing we need to keep in mind, though, is this is actual real data. The points were actually observed, and thus we consider this influential more than an outlier. And we should retain it in the analysis, but we also want to see how influential is this particular point. So to do that, here's what the data looks like again. This is observation 16, so we're going to take that one out and rerun the analysis. So when I do that, what I see is that environment still stays significant. My value, or X, the covariate, still stays important, so that all works. But what I want to look at are my parameter estimates. I see the intercept is much bigger. It's 3 times in magnitude than it was before, and it's also positive. So I have a huge swing with regard to the intercept. My slope decreases by 15%, so it went from 0.65 down to 0.55. And the effective lagoon decreases by 20% from point, I believe 145, something like that, down to 0.125. And that's not surprising considering the intercept shifted so much. So that effect isn't necessarily that big of a deal. But the fact that the intercept flipped around might be kind of a big deal. And aside from the intercept, the direction remains the same. So that everything's still saying it's a positive association with regard to X, and that lagoon is higher in value than, on average, than is the lake environment for oxygen consumption. Now, this switching from positive to negative, if you really go back and look at where that point was, down low and to the left, isn't really surprising, because that point is pulling that line, the regression component, down. It's rotating it down to that, so it makes it steeper. And by making it steeper, changes where the y-intercept is. Now, the other thing that we don't necessarily worry about too much here is that the intercept at this moment is not even interpretable, right? Because we don't see any fish of 0 weight, because I wouldn't have a fish. All right, but we do need to check to see how our fit goes. The fit, it still see a little bit of separation here, a little bit of separation here, a little bit of separation here. So from previously, normality doesn't get much better, but again, we only have 22 points, or now 21. So it's really hard to detect normality or not normality. So unless it's a real huge swing, I would say it's probably okay. Symmetry is still reasonable. By removing number 16, or observation 16, our median does tick up a little bit, so we're a little asymmetric. Our median's just a little above 0, but it's not horrible. And we see that getting rid of that point also made our pattern in our residuals look a little more random, or a little more shotgunny, with the exception of maybe this one, but everything else looks pretty good. So you could say constant variance may still be questionable, but based on the sample size, it's probably not horrible. So if I want to look at a visual comparison between what ANOVA was doing and what ANCOVA is doing, my ANOVA, again, is literally just fitting a mean to each one of these groups, whereas my ANCOVA is fitting a sliding mean based on the covariate value of natural log of weight. So I'm accounting for the size of the fish in the amount of oxygen it's consuming. So if I look at this point and this point are the exact same point. If I come and look at this residual from here to the line, it's really big. If I look at this residual to its line, or its expected value, it's big relative to everything else, but it's smaller than it is in ANOVA. When I come over here, this point and this point are the same. Well, if I look between here and here, this distance is almost twice the size of this distance between here and here, and so on. So basically, by accounting for this, by putting a line in there that's not just flat but actually has some slope to it, I am minimizing the amount of unexplained error. And by minimizing the unexplained error, I increase my precision. Increasing my precision allows me to find smaller and smaller differences. And that is the goal of ANCOVA. ANCOVA is there to account for a covariate so that you can actually increase your precision to be able to find differences between groups that would not normally be found by using just a traditional ANOVA. Okay, now I'm just going to touch on centered ANOVAs. What a centered ANOVA does, or centered ANCOVA, excuse me, what it does is rather than using the covariate as measured, you subtract the aggregated sample mean. So across all groups, you find the mean covariate value. Then you take the observed covariate value, you subtract that mean off from every one of them, and that gives you an average covariate value of 0. Once I have an average covariate value of 0, I've now centered everything, and my line goes on the negative side of the covariate and the positive side of the covariate. But what's nice about that is now the y-intercept has a biological meaning. But by doing this centering, all I'm doing is shifting location, so the slopes and the effect of a differing slope does not change. So when I run on the centered, and you can go through and do this in transform, calculate variable, and plug this in and calculate the center for your data, and have it and go through and do this analysis. If I look, my centered value is still important, 0.001, and my environment is still important. Matter of fact, these are the same sums of squares we saw previously. If I come down and look at my parameter estimates, it even becomes more clear is that my center is still, the effect of the covariate is still 0.55, even though it's a centered covariate. And the effective lagoon is still 0.125, but now my intercept has changed. And what has happened here is my intercept now is 1.438, which happens to be the estimated mean response, if you will, for a fish in a lake environment at a covariate value of that's equal to the mean. So my simple ANCOVA model was 0.191 plus 0.125 times lagoon. So only if I'm in a lagoon does the 0.125 get added on, plus 0.55 times the natural log of weight. My centered ANCOVA looks very similar, only that I have this change in my intercept, and I'm not multiplying my 0.55 times the natural log of weight anymore. I'm multiplying 0.55 times the natural log of weight minus the average of all the natural logs of weight. So again, 1.438 is the model estimated mean of the natural log of oxygen for a white fish in a lake environment at the average covariate value. And the 1.563 is the model estimated mean natural log of oxygen consumption for a white fish in a lagoon environment at the average covariate value. And if you go back and look at the very first table that we, or very first ANOVA we did, the mean for the, just the straight up arithmetic mean for the natural log of oxygen for the lake environment was about a 1.45-ish. Now remember, we took one observation out so that these aren't going to match up exactly. And we ended up with about a 1.55 for the mean natural log of oxygen for the whitefish. So the one point that's always on a regression line, if you will, is x bar comma y bar. And you see that that's kind of coming through here. And the only deviation is really the fact that we're fitting an extra piece, if you will, compared to a regression model coming through as our tau. Okay, so ANCOVA best practices are that you need to verify that there actually is a linear relationship between the covariate and the response. It's best to do this with different colors, so you can, so if you do see a blob, you can actually try to figure out, okay, are the colors lining up in a line, or are they all, is there no point in doing this? Centering the covariate rather than using a simple ANCOVA results in a y-intercept with a physical meaning. Is it required? No, but it makes your parameter estimates mean something. So sometimes it's preferable. As with ANOVA and regression, you need to check your assumptions. Again, it's a constant variance assumption. We still have the normality of errors assumption, and we also have this influential point slash outliers. We need to look at those. And we need to do, like we did here, a sensitivity analysis. How big of an impact do those influential points slash outliers actually have? And if none, you know, you kind of present both, saying, hey, we did a sensitivity analysis. All conclusions remain the same, that kind of thing. And if anything, if you're trying to do this on your own, and if anything is amiss, so you're going beyond kind of a simple, even if you're getting into ANCOVAs where you're trying to test for common slopes, I highly recommend that you seek somebody that does this, you know, on a more daily basis. All right.